All right, hi. Today I'm going to be talking about GPU occlusion. In this talk, I'm going to break down our adaptation of GPU-based occlusion culling using a hierarchical set buffer, and the results that it has led to in our project, in our client's project. Now, first a quick intro. My name is Leon Brands. I am a graphics programmer at Behavior Rotterdam. We are a part of the larger Behavior Interactive, and our studio primarily focuses on code dev. I've been here about 1.5 years now, and in the industry for about 3. And optimizations are my bread and butter. I spent years optimizing a custom multi-GPU ray tracing engine for VR. And nowadays, I spend most of my time optimizing our client's project for their upcoming Switch release, trying to squeeze out every bit of performance I can. So today, we're going to be talking about why we integrated GPU occlusion. We're going to talk about the concept or the idea behind how it works, and the practical application with a more in-depth breakdown of the math involved. Finally, I'll show you the impact it has had on the project, and we'll talk about some of the flaws with our current implementation. So why? Why did we bother with GPU-based occlusion culling? Why would we go through all this effort, and maybe why should you? So the challenge here, the project, as I've described, is code dev. This means that we work side by side with our client while they're still developing the game. In that process, we are primarily responsible for porting the game to PlayStation, Xbox, and Nintendo Switch. And at this point, the game sort of runs on all platforms, but doesn't always hit performance targets. So a large part of my workload is optimizations. Now, we have rather limited control over the code base, and we have no direct control over assets at all. For the game itself, the game heavily features user-generated content. Players can create and design their own levels using pre-authored chunks of content. As a result, we can't easily do any form of baking. On top of that, the engine isn't designed with baking in mind either, meaning that we have no reliable way of detecting whether an object is non-moving or static. Now, when I joined this project, I was presented with a bit of a challenge. At the time, we had a functioning port for the Nintendo Switch, but it ran far above target. Now, for Nintendo Switch to run at 30 FPS, you are looking at a 31 millisecond frame time. But at the time, with post effects and volumetric fog disabled, we were looking at 41 milliseconds. On top of that, the CPU was also struggling, and our memory was heavily exceeding our budget, which somehow is the understatement of the year. So in short, we needed a bit of a miracle. We needed something that improves GPU performance without impacting the CPU and without any form of baking or fundamental engine restructures. So here's the concept, which is largely built on the idea of reusing data is free. In this case, we're using the depth buffer. Now, obviously, the depth buffer is already hard at work, preventing individual fragments from being rendered. And using a depth prepass, we reduce overdraw, and we also use the depth buffer to determine which lights can affect the current geometry. But we can use the depth buffer for more. Using the depth buffer of the previous frame, we can actually try to prevent drawing geometry in the first place. How do we do this? The concept is to project the objects as ABBs onto the screen. And then if an ABB is further away in depth than all the pixels in its area, it can be considered occluded. Now, an immediate concern you might have with this approach is that for that to work, you'd have to sample a rather ridiculous amount of pixels. And we can't just check for random points or corners, because you might miss a gap in geometry somewhere, and an object might pop in and out of existence, which is not an experience you want. So to solve that, we can use something called a high Z buffer or a hierarchical set buffer. This is a depth buffer with runtime-generated MIPS. Each MIP bilinearly picks the largest, so the furthest value in its area instead of the average value. Now, this means that a single pixel at a higher MIP level will actually represent the furthest value in a larger area. For example, in a 1024 by 512 high Z buffer, at MIP level 4, each pixel is going to represent 16 pixels, or well, the furthest value in 16 pixels. This means that with very few samples, we can now get the furthest value in an area, which is going to be perfect for very cheap and quick depth comparisons for our ABBs. In practice, this is sort of what the generated high Z buffer looks like. As you can see, the further we go into MIP levels, the sort of like we keep picking the furthest value until we end up at, well, just about the outside. So how does this work out in practice? Here is a super quick breakdown of our frame. At the start of the frame, we collect our objects. Then we use them to draw the depth prepass. Using that depth buffer from the prepass, we can run the occlusion culling pass. And after that, we can do our base pass and post effects and anything else that I haven't mentioned that isn't as relevant right now. So, in the first step, we want to collect our objects. Now, this obviously creates a bit of a chicken or the egg problem because the depth buffer, which is used for occlusion culling, is generated by the prepass. But prepass is also one of the passes that can benefit from occlusion culling the most. So ideally, we want the data now. This means that we're instead going to be using the data from the previous frame, which can produce some artifacts that I will talk about a little bit later. So the occlusion culling from the previous frame has resulted in a buffer of U&8s, which just with a 0 and 1 determined whether or not an object is visible, and then we use some other numbers for error codes. We start off by collecting all the objects in our frustum, and obviously skipping anything that is out of range or out of frustum, etc. Then every object receives an index or has an index. This index is used to read the culling results from the previous frame, and after that we use it to register the data for the next frame. So we can read out the results from the previous frame to determine whether the object is visible, and after that we can generate a new ID or index into our input and output buffers, and we use that to store. We use an atomic counter here because much of our object collection happens in a multi-threaded fashion, and well, this keeps that nicely safe. Then at this point, we've collected all of the objects that we consider visible using the occlusion culling results in the previous frame. So then we run a simple depth prepass where we just draw our objects without fragment shaders and generate our depth buffer, which looks something like this. After which, we can use the depth buffer to generate the high Z buffer. So for that, we iterate over every MIP of the high depth buffer, and we take the previous MIP and well, take a couple samples and keep the maximum value, which results in the high Z buffer that we've seen before. This is relatively simple code. You just gather, which just gets 4 samples, and take the max value, and we output that into our depth buffer. Now this is maintained as an actual depth buffer for because we use it as we use the high Z buffer as an actual depth buffer for some other passes in our engine as well. Finally, at that point, we can compute we can run our occlusion calling pass, which means that we prepare some of the data, we prepare the ABBs that we've previously gathered. All of the ABBs surround the object in world space and have been passed on to the input data. We bind our resources, and then we dispatch the compute. Now, before we get into how this data is actually used, I'll super quickly cover some efforts to keep it stable. When I initially started working on this technique, it had already been attempted by a previous colleague and had been tweaked a couple times, none of those resulting in quite pleasant results. Some of these, to sort of help you keep some of this stable, what we found was that it's incredibly important to clear IDs when objects aren't considered for calling, because these IDs get carried over to the next frame, and most of the official artifacts that we saw were from accidentally forgetting to clear an object ID properly. On top of that, we highly value visual stability. So if nothing goes wrong, and if something somehow does, we pretend that it doesn't. This means that if somehow occlusion calling takes longer than a frame, we pretend everything is visible. If an object doesn't have an ID, we pretend it's visible. If the occlusion calling shader somehow returned an error, we pretend it's visible. Because the small potential performance trade-off is not worth possible visual artifacts. Now, how does this work out on the GPU side of things? So on the compute side, we'll start with a very simple compute shader, which we keep nice and simple linearly. So we have 64 threads. Every thread is going to receive one ABB that it needs to process. We have a structured buffer containing the ABBs that we've previously gathered on the CPU side. And we have the texture 2D representing our high set buffer with all of the maps that we've generated. So each thread handles a single ABB and then also is expected to write an output, whether it's an error or an actual useful result. So each thread fetches one item from the structure buffer, which contains the ABB data. And from that, we can calculate the ABB size, which we can then use to compute the corners of the ABB in world space. After that, we can run a function here, which is going to take those positions. It will take each corner, and it will transform it and project it into screen space, or clip space specifically, UV space, sorry. It will convert it into UV space. And from that, we can keep the minimum and maximum XY values and the closest set value. And this will effectively generate a screen space UV square that fully encapsulates the object in screen space. On top of that, it will generate the closest set value of that ABB, meaning that we can figure out what part of the ABB is the closest to us, because that will matter for our depth comparisons. Right, so now that we have this shape encompassing screen space square in 0 to 1 UVs, the next step is to figure out a MIP level on our high set buffer, in which our square can be depth tested accurately with the least number of samples possible. For this, we'll be using a point sampler, because we care about the precise values of our depth buffer, which means that if our square covers multiple samples or multiple pixels, all of those need to be sampled. To match those requirements, we're going to compute a MIP level in which our square can be represented by one sample per corner. This means that each sample needs to cover at least half the squares in size. Now, we can compute a matching MIP level by converting the square size to pixels and taking the log base 2 of its largest dimension. This effectively lets us calculate how many times we need to divide the square size by 2 before it fits in a 2 by 2 square, which is exactly what our MIP levels also do. So for example, in this example, our square is 0.01 by 0.005. This means that its largest dimension is going to be around 10 pixels. Now, the log base 2 of that is 3.356, which, after rounding up, results in 4, which is going to be the MIP level on the right here. Now, you might be wondering at this point, is that the correct MIP level? So our high set buffer at MIP 0 starts at 1024 by 512. We start at one sort of like the nearest size, the nearest power of 2 downwards from the original screen buffer. So this is from a 1920 by 1080p render buffer. So let's say our square is an imaginary model that we want to place, draw there, in front of the plant, but behind the square, behind this chair. So why can't we go to MIP level 3? If we were to go to MIP 3, each sample would cover 8 by 8 pixels, meaning that our 10 pixel wide square would have pixels left unsampled in the center. Now, this is a great example here with the chair, where if we were to sample the corner of this square, we would actually consider this square to be hidden by the chair, but in reality, there's gaps left in the middle of it. So what's becoming very clear is that sampling too low of a MIP level might mean that we don't account for gaps in geometry, which could cause objects to appear and disappear when they shouldn't. Now, at our computed MIP level, MIP 4, which has a resolution of 64 by 32, which means that each pixel is representing an area of 16 by 16. Now, as you can see, at this MIP level, the height buffer has sort of like started ignoring the chair's geometry parts, and as such, And as such, in this case, the square would correctly be visible. Now, the pot's depth does remain, and as we've established, we were trying to draw the square in front of the pot. So in this case, the square is correctly visible. But now, if we were to go to MIP 5, we'd end up covering a larger area than necessary. At MIP 5, the MIP level is 32 by 16 pixels, which means that each pixel relatively represents 32 by 32 area. Now, with this square, that doesn't end up affecting us negatively at all. The area still, after all, is still covered by the plant pot, and the object is, it is still going to be visible. But if, for example, the square would have been closer to the edge of a pot, what might have happened is that if we were to try, for example, to render the object behind the pot, and we might have accidentally considered it to be visible when maybe it didn't need to be. So taking too high of a MIP level isn't the worst thing that could happen, but it certainly would result in more false positives than necessary. Right. So having calculated the MIP level that we need to sample our high set buffer at, we can sample these squares corners. We're going to use the previously computed min and max of our square to determine the exact sample points, after which we can figure out what the furthest pixel is on our high set buffer in that area. And then simply, if if the closest value of our ABB is further than the furthest pixel that we've sampled, then we can confidently say that the object is behind another object, or behind multiple other objects, regardless it's occluded. Of course, we don't like if statements in shaders, so it's going to look a little bit more like this. We also do add a very small bias because we found that some very thin objects can sometimes just barely not make the cut when they shouldn't. Right. Let's talk about what this technique has resulted in. Flaws. So I'll quickly cover some of the flaws that we've noticed. As I've discussed, this technique uses the previous frame's data because currently we use CPU to GPU or GPU to CPU interop, meaning that we need to wait for the data to actually be available, and we can't have our frame waiting for that on the GPU side, so we have to carry it over to the next frame. This means that in some cases this can introduce artifacts because the slightly outdated data might not always be accurate. So, for example, if you move through a wall or some very quick rapid changes happen on your screen, it's possible that objects get occluded when they shouldn't. It is only one frame delay. After that one frame, it sort of resolves itself. In our case, we found that there aren't enough sort of cases where that is a major problem in the game that we've been working on. So in our case, it's not a problem, but it can, mileage might vary. Other than that, the occlusion culling approach I've described can also result in some false positives. Particularly with large ABBs, as we take the closest value to the camera, but in some cases, an ABB may, for example, extend behind the camera. And in that case, it always is considered to be as close to the camera as possible, which means it's always going to be in front of stuff. Luckily, that only results in false positives, which we'll take for granted. A couple of false positives is still much better than rendering everything. Right, so for the actual results. On the Nintendo Switch, this technique only takes 0.03 milliseconds, yet it saved us a total of 4.7 milliseconds. Now, this doesn't just work on the Switch. This technique has also resulted in major performance improvements on the PlayStation 5, where we saved around 2 milliseconds, and on the PC, where we saved about 1.8. Now, these numbers, of course, differ depending on sort of what scene you're in, but the game that our client is working on is very heavily sort of like dungeon delve-like, with lots of rooms that don't have vision on other areas. So in our case, it was highly beneficial. And thanks to the flexible sort of ABB-style design of this system, we didn't just use this for meshes. We also extended this to foliage, particle systems, fog volumes, water. Since making this presentation, we also use it for decals and lighting as well to sort of limit how many lights we consider. Which all in all increases the sort of like passes impact, because the less we render, the better. Now, that was my intro to GPU Occlusion. I seriously doubt that I've used up all my time, so I'll happily take any questions.
So if there are any questions, just raise your hand. And if there aren't any questions,
hi, good talk.
Thank you.
It's good, thanks. Did you run into issues with camera cuts and things like that, where the discontinuity from frame to frame?
Very occasionally. We noticed that it's much more noticeable at lower frame rates. So the Switch does sort of suffer from that a little bit, but that's kind of also a trade-off we're willing to make. It's occasionally noticeable if you, for example, move through a wall or if a very rapid change in scenery can sometimes cause objects to still think that they should have been hidden when they aren't, when they shouldn't. But in our case, we've sort of determined that that's just a price that's worth paying for the performance improvement.
Hi, nice presentation. What kind of percentage of your frame was those 4.4 milliseconds?
So I believe that should be around 10%. The vast majority coming from the pre-pass, or the early depth pass, and also some of it actually coming from the lighting pass as well, which still needs to render some of the objects. And especially on Switch, we found that anything that reduces bandwidth usage is fantastic.
Are there any other questions? If not, then I wish everybody a nice break. And
Thank you.
let's see.